All right, so we're here today to talk about essentially probably the fundamental, most important measurement, quantitative, that we can use in thermodynamics, at least in terms of chemists, and that is Gibbs free energy. So we're going to take you on a little tour here of my notes, and you should take out your read along or follow along, whatever I've been calling it. Basically, the notes that I have of these slides, we're going to add to them. A good way to kind of stay awake. And if you can write as fast as you're going to play me on YouTube, then you can go ahead and do that. So we kind of left off in our notes, and you probably should have the old notes out, that we defined enthalpy. Okay, and that's certainly a value that we're going to be able to use to come up with this something called Gibbs free energy. So enthalpy here is something that we talked about that came from if we have constant pressure. And with constant pressure calorimetry, we were able to come up with our values of enthalpy. And there they are. Okay, and essentially what we found that's very important is our state function is equal to a path function. And so we're able to take the energy we get from calorimetry and apply it to a state function. Remember that this, though, has a quantity of kilojoules per mole of the compound, where this will normally just be joules. Okay, so we did all of this already, and again, the bottom line in all of this was that the delta H equals the Q. So this page not really important, okay? And then we went through measuring using delta H's through heats of formation, all right, and so forth. And then we used the chemical reactions through Hess's law, okay? And we've been through this, all right? So there's an example of Hess's law with heats of formations, and then Hess's law with chemical reactions, okay? And in any case, we left off with this discussion of bond energies. And if you look at this, is probably your first slide here of the new part of the read-along. And so what we have here is a great little diagram I like to think about. And so if you take propane and oxygen, and this would be the heat of combustion, by the way, as I try to burn something. So my reactants have this amount of energy, and if they're going to burn, that means they have a lot more potential energy than the reactants. So you already know we're going from high to low, the products, and so it's exothermic. But we can get to that position and measure the change of where we start in energy with where we finish, okay, by using bond energies. Now, before we did that, we were doing heats of formation, what I call the free atom zone. I call it the FAZ, where if we break all our atoms up and we do heats of formation, we can measure all of the sum of the heats of formation of the reactants, and we can do the same thing with heats of formation, the sum of all the heats of formation of the products, and then we do the products minus reactants. Why? Well, a bigger negative minus a smaller negative, okay, will give us a negative number. And we want to show a negative number because we're going down in energy. Delta H is negative. And of course, that was one way. One way to use this Hess's law is to use reactions, formation reactions, or synthesis reactions, where we took the known elements and made the compounds. And from those reactions, we were able to find the delta H of other reactions. That's pretty cool. And we've done that. We talked about that. But the other part of that now is we can use bond enthalpies. So bond enthalpies, we can look over here, here's the energy it takes to break. Now bond enthalpies, unlike heats of formation, are positive. And they're positive because it takes energy to break a stable state. And delta H's of formations are negative because when we take the free atoms of the zone, FAZ I like to call it, and bring them down into the bonds, well, they become stable. They lose energy. So we're just going a different way with bond enthalpy. So we take a table of bond enthalpies. Now we're going to have to look at the individual components of these and figure out what their bonding is like through Lewis diagrams. We can add all the bond energies up and we'll get up to the FAZ zone. And then of course we can actually do the same and take all the bond energies of the products and go up. Now I changed the arrow going down because the way to think about this formula is, in my opinion, we want to have a negative delta H because energy is going down overall. To show that, okay, these bond enthalpies are positive values. They really measure how much it takes to break the bonds. But it's the same energy that's released when you form them. In any case, these are two positive numbers. So if I'm going to get a negative number, I'm going to have to take the bond energy of the what? of the reactants minus the product. So in this case, unlike heat of formation where it's products minus reactions, we use the convention. And the way to remember that, okay, and you want you to write this, is the change of the bond energy of the reactants, the sum, and I want you to write this now in that blank space, the sum of the bond energies of the reactants equals the summation of the sum of the bond energy of the products. And the reason why it's flipped in this case is because of the convention. These bond energies are all positive. So if something's more stable, their bonds are stronger, so it takes a lot more energy to go up this way to the fast zone, to take them and break them apart, okay? Now if you notice, I have this arrow pointing down, because the way to remember this is it takes energy to break bonds, and energy is released when you form them, okay? So the bond energy to break them is the same energy as you release to form them. So I'm showing that, and that helps me remember, hey, here's my reactant, here's the energy I need to break them, here's the energy I need to release to form them. And if there's more energy released in forming them, it's exothermic. So again, by convention, bonds broken minus bonds formed, which happens to be bond energy of the reactants minus the bond energy of the products. And I'm talking about this because people get this wrong. They always think, oh, it's products minus reactants, not with bond enthalpies. Of course, the one we're so used to doing, as I did first, is the heats of formation of the products minus the heats of formation of the reactants. That is flipped. And why is it? Well, for the reasons I explained, because they're both negative, so we'd have to do this bigger negative minus a smaller negative to get a negative value overall. So it's a convention that we use to make sense of the thermodynamic change of delta H. So you should put those two in. All right, moving forward, we know that enthalpy and intermolecular forces are definitely connected. We have heat of dilution, heat of solution. Heat of vaporization is the energy it takes to actually vaporize a substance at its boiling point, and a heat of fusion is the energy needed to melt something. Okay, in any case, they're all different forms of the same thing, heat of formation. All right, now we're getting into the crux of today's basic lesson, is that we're talking about order and disorder. And one of the things I talked about in AP Bio, or just in general, your biology teacher, is that life is very structured and ordered. There is nothing more structured and ordered or important as DNA. Of course, the code of the base pairing in DNA is essential to be an exact, okay, form for us to have the right amino acids being produced to make the right enzymes so that we can show the right alleles. Bottom line is, if we're not making an exact duplicate of our DNA and cells divide, we're going to have some serious problems with the survival of our organism and eventually our species. So life is constantly putting things in order and taking a lot of disorder in to make order. And so that kind of goes against how the energy or the pathway of the universe goes. Now we're talking about this, well, because very similarly, the idea here is that we're talking about pathways. Delta G, Gibbs free energy, that I'm trying to measure here in this lesson is tied to the idea of molecular order. Now we're going to hear the word entropy, we're going to hear the word molecular order, but all of these things really are talking about the dispersion of energy. When I take things and put them in an ordered state like this, these molecules being so ordered and structured, okay, lose a degree of freedom in the process. If you think about these atoms, every single one of these atoms, these nitrogens, these carbons in this organic compound, these guys would rather be a gas flying around and having more independent freedom. These guys can wiggle, but they can't move as freely as they could if every one of these atoms was a gas. So you would say that this form here is a concentrated source of energy or potential, because all of these atoms could potentially fly around as a gas and have tremendous amount of disorder or dispersion of energy. So in this form, we're basically in a concentrated source that could potentially give us a lot of energy. So right now, okay, compared to being a gas form and every one of these atoms having a better degree of freedom, this is a low state of entropy, a low state of disorder. And again, people have used that word kind of incorrectly. We're talking about the dispersion of energy. It just so happens that order and disorder parallels that discussion. So moving forward, spontaneity we talked about earlier in the year. This is important. We talked about when we started our discussion with redox that a battery works a voltaic cell because The redox reaction is spontaneously going. There's a pathway for electrons to be passed around. And that spontaneity is based upon, again, a pathway. All right? It has nothing to do with how fast the reactions. A can of gasoline will react with oxygen given, of course, a spark. But just because it's sitting in a container and not reacting doesn't mean it's not spontaneous. Spontaneity is there a place where this reaction can occur under a set of conditions? And certainly gasoline will burn at most of the conditions we live under. It's just that just because it's not or not going fast doesn't mean that it's not spontaneous. You got to forget the idea that the rate of reaction depends on spontaneity. Okay? So spontaneous would mean a reaction that's definitely going. So we can measure, and that's what we're after with this Gibbs free energy. We want a value that we can measure that will tell us if in fact there's a pathway for reactions to react. So if you see a reaction like this that I have done in class or not, the I dream of Genie reaction, if the forward reaction is spontaneous, that means the reverse is non-spontaneous. What it means, if there's a tremendous pathway for this reaction to go forward, that means the reverse is ultimately very limited, right? So the more spontaneous we go forward, the better the pathway. That means that there's not very good chance of the reverse happening. We talked about this in acid and bases. If I've got a strong acid, this is not an acid though, it's a strong acid because it completely dissociates into protons. And the reason why it's a strong acid, because the conjugate base, what's left over, has a bad ability of doing what? Going in the reverse. It's all tied together. Just like if you burn a piece of paper. You know that burning a piece of paper or wood, it spontaneously reacts, meaning there's a pathway for it to go. CO2 and water are the products. You never see gas molecules, CO2 and water, reacting to reform the paper. That's non-spontaneous. So it's important we get that idea. All right. Now, people think that spontaneity, that pathway, is tied to being exo or endothermic alone. It's tied to this endo or exothermic idea, but not entirely. People think things that are exothermic release energy and go lower in energy. So if I become exothermic, from exothermic reaction, we're giving off the extra energy and getting lower in energy, so that would be a more stable state. We've been talking about this. So you think that's a major pathway. That's true, but there are endothermic reactions that occur. Okay, so certainly water freezing, okay, is an exothermic reaction because liquid has higher energy than a solid. Solids are in a crystal, they vibrate less. So this is an exothermic reaction. Notice the negative value here. And then of course, the energy to melt, okay, is positive because solid needs energy. Both of these this one is endothermic, right? Melting requires energy and freezing releases energy. They both occur. Obviously, we see water melting and freezing. So endothermic and exothermic, although there's a point to this that's very important, is not the end-all be-all, okay? They both can occur, so therefore there are pathways. So being endothermic alone or exothermic isn't what we're after here, but it's tied to it. Okay, molecular disorder. Well, we definitely know that if I have a pure gas here, we've dealt with this NO2 gas in class, okay? When we basically put nitric acid onto copper, this was an NO2, a result of the redox reaction. But if I have pure NO2 gas here and an evacuated flask, once I open it up, what's the pathway? The pathway is for these molecules to move to the left. It's not going to go the opposite way. What I mean by that is it's very spontaneous for it to move this way. Well, you're never going to see them all move to one side to recreate that. So if something's really spontaneous in one way, it doesn't occur the other. We call these types of reactions or processes completion reactions or completion. This is not a chemical reaction, but a completion process where the reverse is almost can't happen. Okay, so the greater the pathway one way, the less the other way. And of course, we know from previous problems I talked about, or ideas or concepts, is that this idea of spontaneity is better, or is better when it's farther away from equilibrium. So as I open up this valve and some of these molecules move over randomly, the spontaneity drops until it's zero when we're at equilibrium. Okay, so we're going to learn that spontaneity is better the farther away we are from equilibrium, something we've touched upon also in our redox formulas. Okay, now we're getting somewhere. Now, energy and disorder, and this is absolutely important to understand. They love to talk about disorder in terms of entropy, but it's about the dispersion of energy, and this is really important. So we take water, and we know when water freezes, we're going from a lot of degrees of freedom of individual water molecules, and we would say a high state of disorder, into a crystal former, a low state of disorder, and we would say that the entropy change, the change in disorder, okay, is going negative. It's decreasing. We're becoming less random. And the reason why that works is because we're taking this free random motion molecules of water that have high degrees of freedom. They can rotate in all directions. And now we're locking them into a crystal where they can only what? Vibrate in their relatively fixed positions when they H-bond to make ice. So we're basically taking the free motion energy, dispersed energy, and we're basically pushing it into a smaller area and confining it. We're going against a major movement of the universe. The universe loves to have energy dispersed. So how can that be? How can I take a system of free moving molecules and make them have order and go against this idea of dispersion of energy? Well, it must mean that enough energy was what? Released in the process, that the surrounding molecules had enough extra energy that they dispersed so much, that they released so much energy that the increase of the disorder of these faster, higher energy molecules that grab the heat is overcoming the loss of entropy here. It's kind of a coupling idea. So the only way this works, because the driving force in the universe, and this is the second law of thermodynamics, is that we must increase the amount of disorder, or better yet, disperse the energy of the universe. Entropy, okay, has to increase for the entire universe. Well, if water is freezing, we're taking these randomly motion molecules and locking them into a solid. The entropy of the system is decreasing. That's not very good. But if we release enough heat to make the surrounding molecules move fast enough, it can compensate for this bad entropy here, and this must be good enough. And of course, anything that freezes must be exothermic in order for that to happen. If this was endothermic to freeze, then this would never work, okay? So it's important you realize that's where we're going. Energy, the flow of energy, is tied to the entropy of the surroundings, which is tied to the entropy of the universe. So that, remember, Boltzmann we studied, and we learned that he committed suicide because no one believed in his atom idea. He spent so much work developing a constant, thinking about mathematically how many different ways atoms can move, okay? But we can define entropy, okay, and we calculate entropy the best way when we have constant temperature. So we can have constant temperature in phase changes. When we're melting and freezing, we know the freezing point of water is 0 degrees Celsius, and the normal boiling point of water is 100 degrees Celsius. Those temperatures don't change because we're basically converting the energy to potential there. And of course, chemical reactions that are thermoregulated, okay, like an automobile engine, they don't change temperature as well. And of course, the best one is that if the surroundings are so large, so if we light something, a piece of paper on a table, will the room air temperature change? Probably not, because it's so big. So we need to have a constant temperature to do that, okay? Now, Boltzmann defined entropy as molecular disorder, but basically we're going to take it to molecular disorder, molecules, and energy combined, okay? So delta S, okay, and we're going to write this here. Okay, we haven't written in a long time. Okay, this is the next one. Delta S is Q of T over T. So we're writing this down. So delta S is Q of T over T. So this is the thermal energy at constant temperature, and this is that constant temperature. And so we're going to write that, all right? And we're going to go to the next slide, and we're going to find out, we're going to add some more, okay? So moving on, we have this slide here, and again, this slide we're not going to add to, but Q of T is delta S. So the measure of the dispersion of energy. Entropy is really the dispersion, the change of a concentrated source to a more dispersed source. That's what the universe likes, but it could also be the other way. It could be a change of entropy where you go from a scenario like CO2 molecules in the air, and they get carbon fixed in photosynthesis and become a solid. That'd be a negative change of entropy. That's going against the universe. And as we're going to learn, when you go against the universe, you have to add energy to make it happen. Of course, the plant does what? It absorbs thermal or wavelengths of light from the sun to drive that process. Okay, so it's not really important that we understand low temperatures, but the bottom line is the change of temperature, the temperature is constant, so we have the energy change at constant temperature over the temperature of the system, okay? And certainly at low temperatures, when this is low, big changes of Q will change the entropy greatly because you're at low temperatures, things are already at their very low entropy point. And why? Because there's a limit to entropy. The lowest possible part of entropy is 0 Kelvin. Okay, now if you have high temperature, therefore things are at a high motion state. Any changes of Q at a high temperature has a smaller change. But most important, the total S of the universe, okay, is the system plus the surroundings, must always increase if the process is spontaneous. This is important, okay? And I think I wanted you to write this somewhere, all right? So any case, moving forward. Yeah, I see you don't have this slide, but we know that delta S of the universe is 0, and of course, if we have a what? Spontaneous process, which is a pathway, the delta S of the universe increases. And then the whole universe is the system plus the surroundings. Now, the system is going to be the molecular entropy, okay? The surroundings is going to be tied to the heat, as we're going to see. So here's an example. All right, so this one you definitely have. We're going to melt some ice. The ice is going to absorb heat. There it is. So we have a quantity of energy for that. The surroundings is going to be negative because the surroundings lost energy. Okay. Delta S is QT, the Q energy over the temperature of the system. Now this ice and water system's at 0, okay, which is 273 Kelvin. We won't put 0 there. We're in Kelvins, a positive scale. So we take the energy that the system absorbed, it's positive, over the temperature of the system, which is staying constant because we're at a phase change. Ice melting, believe it or not, stays at the same temperature. And we get this Joule Kelvin value for my measure of entropy, my measure of my change of disorder, or better yet, the change of the dispersion of energy. Now the surroundings, they're at 25 degrees Celsius. They don't change as well. Temperature is constant because the surroundings are so big. Losing a little bit of heat is not going to make the temperature change all that much. Now, of course, the value here is negative because the energy traveled from the surroundings to the ice. Ice melting is endothermic. And notice something, all right? When I put this in, I get negative 40.3. You should write that. All right, what's the delta S of the universe? Delta S of the universe is delta S of the system plus the surroundings. Well, the system is 44.0 kilojoules, and it's going to be minus 40.3. Put that down. Why is it minus? Because the surroundings, okay, is losing some energy. Now, wait a minute. Why is it getting negative? Well, it's because of the negative Q? Well, yeah, if you're going to lose heat, these gas molecules out here are going to slow down a little bit, which means they're not dispersing. Their degrees of freedom are less. If they're zooming around, hey, okay, they are more dispersed than slowing down. So if some of the gas molecules give their heat, lose their heat, the negative sign, some of the surroundings must have lost some value of their disorder or their dispersed energy. They're becoming more ordered as they slow down, okay? And you notice they're not the same value. Why weren't the same value? Because they're not the same temperature, okay? So if you notice something, the delta S total is positive, and for good reason. The universe has to increase. If this is going to melt, we must be at a temperature that gives us what? A positive change of the universe. We're never going to measure the universe like this, okay? But we're going to basically understand why a spontaneous process works. It works because the delta S of the universe increases, okay? And we have to evaluate the surroundings and the system. All right. And this is, of course, the second law of thermodynamics states that there is a pathway that energy loves to travel, and basically it states that energy must go from a concentrated source to a non-concentrated dispersed source. So the delta S, that dispersion of energy, must keep increasing. All right. So we have this one, And of course, the first law of thermodynamics is the conservation of energy. This is the happy law. This is the law that states anything is possible. Change of energy, the system is change of energy, negative change of energy of the surroundings, and the work path function plus the Q path, the heat path function can be any values. Whereas the second law is a bummer law, says nothing is possible. Yeah, you got conservation of matter, but we can't convert from work to heat perfectly. There has to be some known, there has to be some definite direction here. Okay, so then the third law is actually kind of a weird law because it's about the S, the absolute entropy, which means the entropy, no change, of the chemical has to be zero when it's a perfect crystal at 0 Kelvin. There's no motion, it's in a perfect low energy state. And that's the third law. So this is the uplifting law where anything's possible, conservation of energy, we can convert energy from one form to the other, yay. Whereas this one says, well, yeah, but you're limited what you can do. And then this law comes says, well, we can't even do this yet, but that's a law. So it's kind of interesting, maybe not. All right, so we have in our tablature not only heats of formation table, we actually have absolute entropies. And what I want you to understand here is entropy is a measure of dispersed energy. Solids have a concentrated source of energy. So we look at the absolute part of a solid, its absolute entropy is going to be low. And the reason why we give it a low value is because it doesn't have a lot of degrees of freedoms, meaning that individual atoms, like we talked about in DNA, can't move much if they're stuck in a solid. But if these solids become what? Gases, look at the size of the entropy changes. They jump through the roof. Gases have tremendous dispersed energy because they can fly around the room independently of each other, where the solid molecules have to vibrate in these fixed positions. So if a solid chemical becomes a gas, we would say the change of entropy increases, and we would say the energy is what? Being dispersed. And the change of H would be positive. That's important. So to get the actual change of entropy, that delta S that we're going to need to do this ultimate best derivation of Gibbs free energy, we can use these tables. And basically these tables were made by basically taking compounds or atoms and taking the energy from 0 degrees Kelvin and figuring out what their energy absorption is along the way to become a gas or a compound. All right, again, it's change with constant, of course, temperature. All right, so anyway, this is a measure of dispersion of the molecule, and it's absolute, meaning it's not about a change. Okay, everything else is a reaction. This is just a measured value for that chemical. So when we have a chemical reaction, we go from H2O liquid to, let's say, H2. H2O liquid is 69.95. And then if we react it to become H2, it becomes 130, we would say, wow, the change in entropy really increased. H2 gas, of course, has more freedom, more dispersed energy than H2O liquid. Actually, liquid H2O that does what? H bond. Any case, so the table is there, and we use this table to go what? To get the change of entropy, we take the total absolute entropies of this table of the products minus the reactant. So if I had H2O going to H2, and I know it's also oxygen there as well, but I'm just going to give you an example, and I can see that it's going up. We want delta H to be positive to show that it's increasing. If I go from, let's say, this chemical here, which is 69.95 to 130, I want to see that delta H increase. So I would do the big number minus the small number, the product minus the reactant. And that's why we use the same kind of law to determine delta S, the measure of entropy from tables. Okay? Now, one thing I want you to notice and write this down is the molar entropies, number 4, depend upon the size of the molecule. So when you compare two gases, the bigger gas is going to have a greater value of entropy because it has actually more degrees of freedom. Remember, atoms are actually vibrating in their bonds. We talked about how greenhouse gases are vibrating and give off infrared radiation by how they stretch and move back and forth between the bond. So if I've got 2 more hydrogens of bond to these carbons, these individual hydrogens are bouncing back and forth with their bonds, so it gives them more dispersion of energy by that extra amount of atoms moving. So the bigger the molecule, comparatively speaking, the bigger the entropy. All right, moving forward, Here we have our values. We have delta S that we just talked about that we can get from tablature, the same way that we can get delta H from heats of formation. They have similar formulas. They are different, but they are products minus reactants. Remember, our bond energies are bonds broken, reactants minus products. Also, we've got this delta G that we can use from tablature 2, but we have to define this, and that's where we're headed. Okay, so these two what we have right now. Okay, so what's spontaneity? Spontaneity, we just talked about, is a measure of the universe's delta S increasing. We can measure the delta S of the molecules changing in a reaction, but how do we get the entire universe? Well, party people, let's not forget that spontaneity is a direction. It tells us whether a reaction really goes forward or doesn't react at all, goes forward a little bit. It's not a rate of reaction, it's a pathway. And so in order to know if the reaction goes, we have to see if that reaction makes the entire universe's energy disperse. So it's impossible for us to just look at how the molecules change in the reaction. So if I go back to my tablature here and I do the delta H of my products minus reactants, the absolute entropies of my products minus reactants to get a delta S change, I can't get a value for the entire universe. I only get it for the molecules in my beaker, okay? So how do I understand the entire universe? So the bottom line here is we need a value, and it's this guy right here, delta G, a new thermodynamic state function that will help us evaluate whether or not a reaction is spontaneous, has a great pathway. And the way that we have to derive this is so that we can measure somehow the entire universe's what? Change in entropy, dispersion. But we can't put monitors out for the entire universe. That's impossible. So somehow we have to do this in order to measure the system's heat changes, and that's key, and what? Individual entropy changes of the atoms. So let's continue on this process. All right, so we're going to turn to this page here in our notes, okay? And we're going to, right now, this moment, okay, as Shania Twain would say, from this moment on, nothing is going to be the same for us. And the reason for that is we are going to define delta G. And delta G is going to be a value that gives us a quantitative value of whether or not a reaction actually will work by measuring the entire universe's entropy. How do we do it? Let's do it. First off, I start with a what? A reaction. Let's make it exothermic. It has a negative Q. That means that the surroundings are absorbing energy. Of course, the delta H is per mole, but the delta H is equal to the Q. Why? Because we're at constant pressure calorimetry. This is open. All right. And what do we know? The delta H of the surrounding is the negative delta H of the system. Has to be. Okay? So we're going to rewrite that right there. So delta H of the surroundings. And what does it equal? Now, you notice I divided by temperature. Okay? And that should be wary why I'm doing that, because Q over T is entropy. I'm going to link the energy change in terms of the heat flow of the surroundings to entropy. That's the key, party people. The energy released, we talked about this in the freezing of water, is going to do what? Change the ability of the molecules and disperse them. Okay? So that's important. So what do we have here? Delta H is surrounding. We're going to divide by T because we want to get entropy out of this. And of course, we divide by the temperature. And of course, it has to be at constant temperature because this only works at constant temperature. Notice something, I had delta H of the system over T. They have to be equal to each other. Okay, delta H of the surroundings is negative delta H of the system. I'm going to divide by that constant temperature of both. Okay, now when I do that, party people, all right, what does it give me? Well, I'm just going to rewrite this. At constant temperature, it gives me the delta S of the surroundings. Q over T is the same as delta H over T, and it comes from the energy given off. So we are able, and this is such an important understanding, this is where it comes from. This is the moment of truth here. The energy released is messing around with the entropy or the disorder of the gas molecules. These gas molecules are moving slowly, randomly, And if there's energy released, now they go faster. They're more dispersed. And therefore, entropy has increased if heat is released. That's the key. We're using the energy change, okay, to quantify the energy of the surroundings. So we're just able to measure the what? The system's energy change. Remember, this is the system related to this. So therefore, the energy change of the surroundings, okay, over T is the delta S of the surroundings. Okay, well, what's it equal to? Haha, it's equal to the delta H of the system over T. That's where it came from. Remember, the energy released, okay, is the delta H of the surroundings because of constant pressure. It's equal to the negative H of the system because the system, of course, is exothermic. And then I divide it by constant temperature on both sides. I can do that to an equation. And I get entropy. And I get this kind of expression. All right, we're almost done. So what do I have here? This represents the delta S of the surroundings. I'll let you write that. I want you to write it. This expression, negative H of the system, is the delta S of the surroundings. What's the system? Well, the system we can get from tablature by knowing how the atoms are dispersing from reactants to products. And that's the system. And if we add this value up to what we get from tablature by knowing how the atoms change, we get the entire universe's, okay, entropy. And if both of these wind up making this positive, we have ourselves a spontaneous process. That's the key to the entire thing. Now, we haven't made delta G yet, so let's go to the next page, the most important page. Okay, and this is the molecular disorder we get from the tablature. Okay, so what do we have? The delta S of the universe is equal to the delta S of the surroundings plus the system. Yes, second law of thermodynamics states it has to increase. But to know if something is spontaneous, I need to understand that I can really only measure the systems. So at constant pressure and constant temperature, I can do this. All right, so we've got this idea right here. Delta S of the universe equals this expression plus the system we get from the tablature. All right, so delta S is the change of Q over T. All right, change of S, change of Q. It's constant pressure, so I can do this. Equals this expression here. I'll let you write that. Okay, it's important that you understand. Fundamentally, the most important of all derivations we do. Okay, as a chemist, don't we want to know if the reaction works? Yes. All right, we don't want to blow up trying. We can do it in pencil and paper. All right, so what does this equal? Well, if I multiply by negative T over 1 makes this a negative expression. Just T over T makes this negative Q, which is just energy. Negative T over T makes this, well, the T's cancel, but because it's negative, it just becomes a positive delta H. And then timesing this also by negative T by the distributive property makes this negative T delta S. And booyah, what we have is, okay, negative Q over T. This is free energy equals this times T delta S. And that's our formula, okay? So we get rid of the T's by multiplying by negative T all the way through. And this gives us our formula. We call the free energy Gibbs free energy, okay? Please write that. That is fundamentally the most important thing you can write. Delta G of the system, which is a measure of free energy, equals delta H of the system, how the system changes energy, minus temperature in Kelvin times the change of the molecular entropy of the system using tablature. Look at those systems, party people. Look at them. Look at them, okay? They're all systems. We are measuring the total energy of the universe, the entropy of the universe, by using information from the system. And we can do this as long as we have constant temperature and pressure. And this is pretty cool. Don't forget, we multiply by negative T, so this is a negative value. So what that means is this needs to be negative and keep growing as a negative if we're going to be spontaneous. Okay? Very important. So this form of the energy change gives us the what? The delta H of the surroundings. So being exothermic and endothermic, which we talked about before, is a key to it, but not everything. And of course, just the system changing its entropy, which means that the molecules are going from a solid to a gas or so forth in the reaction, also gives us a clue, but it's the combination of energy changing from the system to the surrounding and the system changing its what? Its value in terms of its dispersions of energy through tablature that gives me the entire thing. Okay, so let's go on to this last page. Okay, and so here's our formula. Okay, now please write this one. All right, now this one I call the always law. Now if you notice, a negative delta H is exothermic. Energy is being lost, okay, overall from products minus reactants. And we're going to say entropy is increasing. A delta S that's increasing is positive. Very good. And this is going to be called the always rule. Now why? Well, party people, okay, if you think with me for a second, if this is a negative, okay, if this is a negative here, let me just write something down. If this is a negative, and this is a negative, and this is a positive. Now this is a positive because entropy is increasing, and this is a negative because it's exothermic. Okay, now what's increasing for entropy? Well, the molecules might be going from like one atom in the reaction, breaking apart into two pieces. Let's say hydrochloric acid becomes H plus and Cl negative. Okay, so they would say that the entropy is increasing by one thing breaking apart into two. You have more degrees of freedom. Okay, what's exothermic? Let's say heat was released in this process. Okay, so if heat's released in this process, we can say is that, okay, the energy is absorbed by the surroundings, and the surroundings are going faster. And our molecules are dispersing their energy by having more degrees of freedom. So that should give us an always, always, always spontaneous reaction. Now, a spontaneous reaction is measured by delta G becoming negative, always negative. Well, let's do the math. Negative delta H, positive delta S. Don't forget this. When we do the math, it's going to be plus a negative. So this whole expression, a negative plus a negative, always gives me a negative number, and it's always spontaneous. Okay, very important you understand that. So exothermic, heat releasing, and the entropy increasing for the molecules, my gosh, always, always a pathway. So what's the negative rule? Well, the negative rule would be, the negative rule looks like this, maybe. And here's a scenario where delta G equals a positive value. Why? Well, now we're endothermic, which means that the energy is going into the reaction. That means that the surrounding gas molecules go slower, and therefore they're not dispersing energy anymore. And our entropy of our system, meaning maybe, okay, two things are coming together, or a solid is becoming a what? A gas is becoming a solid, molecularly speaking. This is bad. Why? Because if you have a plus minus a negative, this becomes plus plus, and a positive mathematically always gives a positive, and that's the never rule. So this is an endothermic process where energy is being taken from the environment and used by the reaction. The environment goes slower. It's no longer being dispersed. Therefore, the entropy of the environment, that's what this expression is, does what? Is decreased, is negative for the what? Environment. And then here, this measures the molecular motion. And let's just give an example of an molecular motion would be, again, two particles coming together to make one. Okay, that would be a loss of degree of freedom, and that would be negative. And you do the math, okay, you do the math, again, if you don't see it, okay, we're going to do the math here, and what we get is we get a plus, plus, and that always gives me a positive delta G, all right? And so this is the never rule. Never happens. And my little cartoon here in the always rule, this if you can somehow use this rolling rock, okay, and have it push a cart like this person, it's going to push this person down the hill without trying. So this person is here, okay, spontaneously this rock is going to move this person, whereas this person has to move this rock to make work. Meaning if your delta G is positive, that means that you're not spontaneous. There's no pathway for the reaction to go. You still can make the process work, possibly, but you're going to have to add energy to make it happen. Okay? And that leads us to the sometimes rule, where it could be positive or negative. Okay, here in this case, we have an exothermic reaction, but so we're releasing heat. That's a positive thing. That means the surrounding gas molecule is going faster. We're dispersing energy. Delta H of the what? Of the surroundings is increasing, but the entropy of my molecules, my molecular from tablature, is decreasing. So they're going opposite. Notice this will be a plus plus, and so this is negative and this is a plus plus. When can it be negative? Well, if the negative is great enough. So if I've got my entropy going against the universe on the molecular side, I need to make sure that I give off enough energy. This is what we call like freezing, okay? Freezing is exothermic and the liquids are becoming a solid. It only works if the temperature is what? Low enough, right, to decrease this negative value. These kind of reactions we call enthalpy driven. If they're gonna work, it's because the enthalpy is big enough, or in this case, more negative enough to make this negative bigger to overcome this positive part, or in this case, the bad entropy part of the system. We have to have enough energy released to the what? Surroundings to overcome the energy or the dispersion, the lack of dispersion of energy in the system. And overall, there has to be enough energy to make the what? Universe increase. So this has to be a negative value big enough. So what drives it is enthalpy driven. Okay. The next one is the opposite. It could be plus or negative. Now we have an endothermic reaction, and the entropy is increasing. So the only way this can work, if energy is flowing from the environment, going what? Now the gas molecules are not as dispersed because they're going slower as energy flows into the reaction. That makes the surroundings drop in entropy. But if the entropy of the system increases enough, so in this case here above, the enthalpy driven, we talk about freezing. Freezing is when a liquid becomes a solid. So a liquid who has all kinds of free degrees of freedom gets stuck into a scenario where it can only vibrate in its fixed position, okay, loses a lot of its energy, or the energy now gets stored into a concentrated place, because now these molecules could be free if they were released, but now we're stuck wiggling in a fixed position. We'd say the entropy, okay, is decreasing here in the case of freezing. So that's bad, but the what? Energy release can overcome that. Now in this case, we have an absorption of energy, like melting an ice cube. We melt an ice cube, energy is absorbed, okay, and that's bad because the resulting gases move slower. However, a solid locked in a crystal becoming a liquid who has more degrees of freedom increases the entropy. If this is a big enough increase of entropy to overcome the lack of entropy change or dispersion from the environment, when you take energy from it, you can make this negative. So this would be an example of entropy driven, okay? So the negative delta G measures whether or not the process, there's a pathway. And the bigger that negative, the more forward the reaction and the more improbable the reverse. This is by far the most important thermodynamic quantity. So if I get a delta H by Heats of formation table and delta S is by the same table or tablature, I can solve for the delta G. Hopefully it's negative, the process works. I can also get delta G from tablature. If you notice from your tables, there's something called delta G of formation, and it's a results with the same formula. So these three formulas, or these four formulas, are now working in unison to help us measure whether or not something is spontaneous, which means there's a pathway, which means there's something called free energy. And if I haven't explained, this Gibbs free energy is called free energy because if there's a pathway, okay, if you're going in the forward direction spontaneously, the reaction is going, we can use the energy of the reaction going to drive a process. Burning fossil fuels, okay, makes our cars work. Burning combustion. So reactions that are spontaneous allow us to do work with them. As I often said, we can ride that energy pony. So these three formulas are our friends, and they are, of course, in our reference table that help us work through all these problems. Hope that helped.